So yeah, let me start by thanking the organizers for organizing this nice conference and echoing what Christian said that I hope that this will be the first of many. So today I'm going to tell you about a model of Weyl Semimetal, a holographic model of a Weyl Semimetal that I constructed in this paper with these authors, including Chasm. All right, so I'll get right into it. So first off, what is a Weyl Semimetal? So a Weyl Semimetal is a very special kind of material in which the low energy excitations are Weyl fermions, and they're Weyl fermions of a kind of emergent Lorentz symmetry. They're quite new, so they were first experimentally discovered in 2015. And here I cite the first discovery, although following this, hot on the heels of this discovery, there were many additional examples of Weyl semimetals discovered, although they were theoretically sort of conjectured to exist well before 2015. And it turns out that Weyl semimetals inherit various interesting properties from topology and also because they have a chiral anomaly. We'll see some of these during the talk. And some of these properties, for example, some of the interesting transport properties that arise lead to hopes that they might be useful, for example, for building novel electronics. And so for us, one of the key features of them is that the Coulomb interaction of Weyl semimetal turns out to be weakly screened. So in principle, there may be strong correlations between the electrons in a Weyl semimetal, in which case you need some non-perturbative tool to study them. And so the tool that we're going to use is holography. Okay, so before I move on to holography, I'd just like to give you a very simple quantum field theory example of a Weyl semimetal that, at least for me, coming from a high energy physics perspective, helped me understand better what they actually are. So the toy model in question is just a free Dirac fermion psi. And you can see in this Lagrangian that I've written down, the first two terms are just the Dirac Lagrangian. And then the kind of interesting term is the third term involving this B. And this is coupling to an axial gauge field. So recall that psi bar gamma mu gamma 5 psi is the axial current. So B is a axial gauge field pointing along the x3 direction. And if you work out the Hamiltonian from this Lagrangian and its eigenvalues, they look like this. So it's a 4x4 Hamiltonian, so there's 4 eigenvalues, and they come in pairs. So you see there's 2 plus or minus signs in this expression. They're uncorrelated, so it gives you 4 eigenvalues total. And the most interesting 2 eigenvalues are the ones where inside the square root, that plus or minus sign is a minus sign. So you have sort of equal and opposite eigenvalues with a minus sign inside the square root. And so now if I plot these, so their behavior depends crucially on the relative size of these 2 parameters B and M that appear in the Lagrangian. But for B greater than M, if you plot the eigenvalues, they look like this. So here I've plotted on the vertical axis energy, on the kind of, let's say, horizontal axis, the momentum in the Z direction, which is the direction along which we had this axial gauge field. And then on the sort of axis into the screen, if you like, there's the momenta in the orthogonal directions. And you can see that the 2 energy bands, so the plus or minus sign in this spectrum corresponds to the 2 different colors, blue and orange, in this plot. So these 2 bands meet at 2 points in momentum space, separated along the KZ direction. And it's the sort of excitations around these points, so we call these points Weyl nodes, and it's the excitations around these points that are these Weyl fermions that I talked about. And now if I increase M relative to B, the locations of these Weyl nodes changes slightly. They come closer together. And eventually when M is equal to B, the 2 Weyl nodes collapse on top of each other, and you just get a single band touching point with quadratic dispersion around them. And then if I increase M further, then the bands no longer touch. So for M larger than B, we have an insulator rather than a Weyl semimetal. So there's some quantum phase transition going on as I vary this dimensionless ratio between these 2 parameters. So how do you know in the small M over B phase where we had these band touching points that the low energy excitations are Weyl fermions? So you can show this by looking at an effective Hamiltonian that describes these 2 bands. So I don't have time to go into detail how you derive it, but I do have some backup slides if you're interested. But you can show that the 2 eigenvalues that I've been plotting, they're just given by, they're also the eigenvalues of this 2x2 Hamiltonian that I've written down here, and where the sigmas are Pauli matrices. And then if I expand near one of these two Weyl nodes to leading order in small kz away from these Weyl nodes, it looks like this. And then if I just redefine my momentum in the z direction, sorry, I don't know why that's just changed size, at least it has on my screen, then you can see that you just get the Weyl Hamiltonian. There's a plus or minus sign corresponding to which of the two Weyl nodes you're at, and that just means that the two Weyl nodes have opposite chirality. So when the excitations around one of them is a left-handed Weyl fermion, and around the other it's a right-handed Weyl fermion. Okay, so this model illustrates some key features of Weyl semimetals more generally. So one is that in this model, time reversal symmetry is broken. And the reason for that is if you just open a quantum field theory textbook and look at how spinor bilinears transform under time reversal, you'll see that this spatial component of the axial current that we had in the Lagrangian is odd under time reversal. So by including it with explicitly broken time reversal. And in fact, to obtain a Weyl semimetal, you must break at least one of time reversal or parity, because otherwise the energy bands are doubly degenerate. And so you'll never get Weyl fermions at the low energy excitations. And so here I've just shown you a table of some examples. So there are known examples of Weyl semimetals of both cases, either breaking P or breaking T. It turns out I think that breaking P tends to be more common, but in this talk I'm just going to focus on Weyl semimetals with broken T. Another feature that you see in this model is that the Weyl points, the Weyl nodes, come in pairs of opposite chirality. So there was one left-handed, one right-handed Weyl fermion. So this didn't have to be the case in this particular model, which was just some continuum quantum field theory, but in condensed matter, we've always got in mind some underlying lattice description of our system. And in lattice systems, Weyl fermions have to come in opposite chirality pairs due to the Nielsen and Nomiya theorem. Another feature of this model that is true more generally is that these Weyl points, these Weyl nodes, are topologically protected. So the two energy bands meet at these points. So it's a point of degeneracy in the spectrum of the Hamiltonian. And so you need something to protect this degeneracy from just being destroyed by small perturbations. And in a Weyl semimetal, the degeneracy is protected by topology of the Berry connection. So just to remind you what that is, if you have some Hamiltonian that depends on some set of parameters, in our case the Hamiltonian depends on the momenta, k, then you can obviously find some corresponding set of normalized eigenstates that depend on these parameters. And that's what the UKs are in this equation that I've written down. And then if you just take the exterior derivative of one of these states and then take the inner product of that with the original state, you get this Berry connection A. And there's some gauge redundancy to do with the fact that there's some phase redundancy. There's this set of normalized eigenstates don't have a well-defined phase, and that's why we call it a connection. And if you integrate this Berry connection over a sphere that encloses one of the two Weyl nodes, then you'll find either plus or minus 1, depending on whether it's a left or right-handed Weyl node. And this has to be an integer. It's an integer called the Chern number. So because it has to be an integer, it can't be destroyed by a small perturbation. And so generally the only way to get rid of Weyl nodes is to bring them together, like we saw in this quantum phase transition, where the two Weyl nodes collapse together to a single point, and then eventually you gapped out and got an insulator. Okay, and then the final feature that I want to highlight is that there's an axial or chiral anomaly in this system. So the chiral anomaly, recall, is just that the divergence of the, sorry, I should really call it the axial anomaly. The axial anomaly is the fact that the divergence of the axial current is non-zero in the presence of some background vector field strength. And you can see that as arising from some triangle diagram like I've drawn on the right-hand side, where you've essentially got one insertion of the axial current and two of the vector current. And this chiral anomaly, or axial anomaly, leads to some interesting transport properties of Weyl semimetals. And the key one that I want to highlight for you is that it leads to a Hall conductivity, an anomalous Hall conductivity, which essentially tells you that when you apply an electric field to a Weyl semimetal that's orthogonal to this axial gauge field, then you'll get a current that's orthogonal to both the electric field and the axial gauge field. And to see why that occurs, you can think about this triangle diagram and realize that it will essentially arise from a term in the effective action, which looks something like what I've written down, where you've essentially got some kind of Chern-Simons-like coupling with essentially two copies of the vector field strength, the source for the vector current, that's this A, and one copy of the source for the axial current, that's this A5. And so the chiral anomaly arises from essentially differentiating this with respect to A5 to get the one-point function of the axial current. But if we instead differentiate this term with respect to A to get the one-point function of the vector current, you can probably convince yourself that what you get on the right-hand side is going to be something like a Levi-Civita symbol contracted with the axial current and with the vector field strength. So you essentially get a current that's proportional to A5 cross E. So this is this Hall current that arises in Weyl semimetals. And so that calculation that I sketched was only true for the case when the fermion was exactly massless. Otherwise, there's an additional contribution to the anomaly. And it turns out if you do the calculation for all masses, you find something like this. So so we had this axial vector field along the z direction. So I'm now imagining applying an electric field along the x direction. So you'll get a Hall current in the y direction, and that's proportional to the electric field, and the proportionality coefficient is called the Hall conductivity. That's the sigma xy. And it looks like I've plotted here. So in the Weyl semimetal phase, that was when m over b was less than 1. It's essentially this semicircle with the square root of b squared minus m squared. And then it drops to 0 at the phase transition and 0 in the insulating phase. Okay. So now I want to move on and use holography. So as I talked about on the first slide, the Coulomb interaction can be weakly screened in Weyl semimetals. And the reason for this is that the density of states at the Fermi level in a Weyl semimetal vanishes. And since the Coulomb interaction screening length goes like 1 over the square root of the density of states at the Fermi level, since it goes like 1 over square root of density of states and density of states goes to 0, the screening length goes to infinity. So you can end up with strong interactions between the electrons. And so practitioners of holography will see this and think, yes, well, let's use holography then. And indeed, people have done so. And there's been sort of two approaches roughly to trying to model Weyl semimetals on holography. The earliest approach was to use what's called semi-holography, where you directly introduce some Weyl fermion degrees of freedom on the boundary, which have strong interactions mediated by some holographic theory. But there's also been a fully holographic approach where just everything is done in the bulk gravity theory. I've just cited some of the earliest papers from these two approaches. So in this talk, I'm going to take the second fully holographic approach. And the key distinction of the model that I'm going to talk about is it will be top-down. So what this means is it comes directly from string theory, so we know exactly what the dual quantum field theory is. I should mention that it's not the first top-down holographic model of a Weyl semimetal. Here I've cited the two other examples that I know of. But hopefully you will agree once I show you the model that it has some nice features, and it's just kind of a nice model. At least I like it. Okay, so the model in question is going to make use of D-branes. We've already seen D-branes a few times today. So in the slide, I'm partially going to be recovering some old ground, but I think it was good to make sure we're all on the same page. So the starting point is to think about the stack of D3 branes, which generates an AdS5 cross S5 geometry and is dual to n equals 4 super mils with gauge group SUN. And we can add n equals 2 hypermultiplets and the fundamental representation to this theory, this n equals 4 super mils, by adding D7 branes to the spacetime, the AdS5 cross S5 spacetime. So I've kind of sketched how you do this here in this table. So I'm imagining putting my D3 branes along 4 directions that I call x0, 1, 2, 3. And I'm placing the D7 branes also along these directions, and then they've got 4 more dimensions, so I'm also placing them along x4, 5, 6, 7. Yeah, I should just mention that I'm typically going to call the common directions shared by both the D3 and the D7 branes T, X, Y, Z. You can think of these as the directions inside the Weyl semimetal in the dual field theory. So there's 2 directions, x8 and x9, along which you can separate the D7 branes from the D3 branes. And it's the size of the separation that determines the mass of these hypermultiplets. So here I've combined these two directions, x8 and x9, into a complex number. And the magnitude of this complex number is proportional to the mass m of the hypermultiplets. I should mention actually, so a hypermultiplet contains a Dirac fermion, that's the psi, and there's two complex scalars as well, which sometimes get called squawks. There's this q and q tilde. And so it's the psi in these hypermultiplets that we're going to think of as the electrons in the Weyl semimetal. So the masses of the electrons are determined by the separation between the D3 and D7 branes. And you can see there's a complex phase as well, which if it's constant isn't too important. You can essentially just remove it by a field redefinition, or on the gravity side by a rotation. But it will turn out to be very important for in our case, because we're going to make phi not constant. And in particular, if you choose phi to be linear in one of the field theory directions, we're choosing phi to be linear in the z direction with proportionality coefficient b, then you can show that the Lagrangian of the dual field theory contains a piece which looks exactly like that free model that I wrote down. And here I write it down again. So it's Dirac Lagrangian plus a coupling between the Dirac fermions in the hypermultiplets and an axial gauge field. But of course, in the Lagrangian, there's many more terms. I mean, there's everything describing n equals 4 Young Mills and the rest of the fields in the hypermultiplet and various interactions between them. So the approach that the philosophy that we're going to take, that we took, or at least I take, is that in this model, the size, the Dirac fermions represent the electrons, and all the other fields of n equals 4 Young Mills plus the remaining fields in the hypermultiplets we think of as just mediating the strong interactions between the electrons in this Weyl semimetal. Okay, so how do we actually implement this model holographically? So here I write down the AdS5 cross S5 solution of type 2b supergravity. So you can see in the metric on the first line, there's T and X, these are the field theory directions. Then you've got R and an S3. These are essentially the additional directions wrapped by the D7 branes. And then the two directions along which you separate the D7 branes from the D3 branes are what I call capital M and phi. And I call that one of those directions capital M because it's proportional to the mass, or at least in the limit that you go to the boundary of AdS, it's proportional to the mass of the D7 branes. Of the hypermultiplets. And so we need to make some kind of ansatz for how these two directions M and phi depend on the coordinates on the D7 branes. So we're just going to make the very simple ansatz that M is just a function only of R, it's the AdS radial direction, and that phi is linear in the field theory direction Z. That's what gave us this axial gauge field that we needed to get a Weyl semimetal. And so what this looks like is essentially what I've sketched on the right-hand side. We have the D3 branes and the D7 branes, and the D7 branes are separated from the D3 branes by some distance m. And then because phi is linear in Z, as you move along Z, the D7 branes are essentially rotating around the D3 branes, so there's kind of a helix, it's like a helix of D7 branes surrounding the D3 branes. Okay, so yeah, I should mention that a similar ansatz has appeared in some earlier works that I cite here, with some differences. In particular, they only look at massless embeddings. Okay, so once you've made your ansatz, you can just substitute this into the D7 brane action. That's this DBI action that Marty had in his talk. And what you end up with looks like what I've written at the top of this slide. And then you can derive the equations of motion for M as a function of R. And it turns out that there's three different kinds of solutions to these equations of motion, as I've sketched here. So they're characterized by their behavior at small r, that's deep in the infrared. The first kind of solution is that M just goes to a constant as R goes to 0. And I've called that constant M0, it's an integration constant, so there's a solution for each M0. Then there's solutions where M vanishes as R goes to 0, exponentially quickly in 1 over R. And again, there's a whole family of solutions parameterized by this constant that I've called eta. So for every eta, there's a solution. And then there's also one single solution with no integration constant where M vanishes linearly in R as R goes to 0. And when you have these different kinds of solutions characterized by their different infrared behaviors, in holography, they're due to different phases on the boundary or the dual quantum field theory. And although I haven't explained why yet, it will turn out that the first kind of solution where m goes to a constant is due to an insulating phase. The second kind of solution where m vanishes exponentially quickly is due to the Weyl Semimetal phase. And the single solution that's where m vanishes linearly is due to the sort of critical phase that separates these two other phases. Right, and so once you've got these deep infrared behaviors, you can just integrate the equations motion out for all values of r numerically and find what the solutions look like. So here I just plot some sample solutions. And recalling that the r goes to infinity limit of m was proportional to the mass of the hypermultiplets, you can see that the what I call the Weyl Semimetal phase corresponds to small mass roughly, and the insulating phase corresponds to large mass roughly, just like in the free model. But I should stress I haven't actually justified for you these labels of insulator and Weyl Semimetal. So we have a phase transition, and to see what kind of phase transition it is, we can compute the free energy, and we can see that there's a first order phase transition where essentially you just have a jump in, well, you have a sort of switch over at some critical value of m over b, at below which the Weyl Semimetal phase dominates the ensemble and above which the insulating phase dominates the ensemble. Okay, so
there's only 5 minutes left.
Okay, great, thanks. Right, so to justify these labels of Weyl Semimetal and insulating phases, we need to compute the conductivities of our system. So to do that, we used a method, it's sometimes called the Karcher-Bannon method, from this paper that I cite at the top of the slide. If you're interested in more details, I've got some backup slides, so if you can check my slides or ask me about it. So it turns out that the longitudinal conductivity, so the conductivity that determines the size of a current parallel to an applied electric field, vanishes for all the phases. But the Weyl Semimetal phase, the low m over b phase, it has a non-zero Hall conductivity. It turns out to be given by the total number of fermions times the m equals 0 result of the free model. And it's actually independent of m for all m in this phase. And then in the insulating phase, the large m over b phase, the Hall conductivity vanishes, so we get the step function-like behavior. But it's the fact that it's non-zero in the low m over b phase, which is why we identify this phase as a Weyl Semimetal. So then the final thing we did was turn on the temperature, and I won't go into details. I'll just say that you do so by including a black hole in the space-time, and then you again get different kinds of solutions, and you can again compute the conductivities using the same method. So here's the Hall conductivity that we find as a function of m over b and t over b. And this thick black line shows the phase transition, and you can see that the small m over b phase always has this Hall conductivity, whereas the large m over b phase always has vanishing Hall conductivity. And then at non-zero temperature, the small m over b phase also has non-zero longitudinal conductivity, whereas the large m over b phase has vanishing longitudinal conductivity. So that's why we identify this phase as an insulator. Okay, so that's all the results that I have time to show you. So just to summarize, so Weyl Semimetals are quite a new state of matter. They have weak screening of the Coulomb interaction, so there's possibly strong interactions between the electrons, and so holography is potentially a useful tool. And we used the D3, D7 system to construct a string theory model of Weyl Semimetal, which had the key advantage that you knew exactly what the holographically dual quantum field theory was. And it was straightforward to compute conductivities in this model, and it sort of reproduces the expected Hall conductivity in the dual quantum field theory. So some outlook, there's plenty of other observables that you can think about computing. For example, you could imagine studying hydrodynamics in this model. One thing that would be interesting but technically very difficult would be to relax the probe limit. And this would be interesting because it would let you study transport of energy and momentum in the system. And another thing, more of a pipe dream maybe, I don't think you could do it in this model, but more generally in holography, it would be interesting to study another kind of material called a type 2 Weyl semimetal, in which these Weyl nodes are tilted over, as I tried to sketch in this diagram on the right-hand side. And they should have quite different physics from the type 1 Weyl semimetals, which was what I was talking about in this talk. But at the moment, I have no idea how you would actually study these in holography. So that was everything I wanted to talk about. Thanks very much for listening.
Very good. Thanks, Ronnie, for your great talk. Let me check if there's any question. Yes, question. Okay. Okay. You can ask your...
Christian here. Thanks for the talk. It was very nice. So I was wondering about this longitudinal conductivity, which you said vanishes in all phases. Is there an underlying reason for that? So it sounds like a very strong constraint.
Oh, so this was only at 0 temperature?
Only temperature.
Yeah.
But is there maybe some sort of topological constraint or anything that, or is that just...
It's a good question. I think it probably comes down to the vanishing density of states in the Weyl Semimetal phase.
Okay.
So yeah, for the insulating phase, it makes sense. In the Weyl Semimetal phase, I think it's probably due to the vanishing density of states. I think it's just a sort of generic feature of Weyl Semimetals, or probably semimetals more generally, that you usually have a sort of linear in T conductivity at low temperatures, which is what we find as well.
Okay, then that makes a lot of sense. Thanks.
Okay.